Hi, I think you're back for my second video, huh? After you heard it. Well, actually, if you haven't heard it before, I recommend you do video 1 first. Because I have a super fun presentation of the first 16 iterations, so I didn't get the photos quite at the same place. Anyway, you can see the difference. Share screen. The Mandelbrot set. Yeah, probably already talked about that in video 1. I'll let you watch it for a little bit. If you need more time, just pause your video. Okay? Yeah, we talked about that already, right at the start. 0, 0, 0, 0. That's the countdown. The count up. 0, 0, 0, 1. This is actually the boundary. 0, 0, 0, 2. 0, 0, 0, 3. You see, it's just getting closer to having a full caridoid. What's a caridoid, anyway? Number 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's all, I guess. Now you can clearly see. I'm going to start at each slide. See how at this iteration we'll stop at here. These are starting to form mini. Well, I have a more clear zoom in. That's all. I added 20 slides. Because I like to call that the 0 iteration. See, the coloring is not really official. The coding is, however, very official. Wait, do you know what happens when I copy and paste? You see a light show. It's very quick. I can't make it slower. Oh yes, sometimes you see a light show. You know how the main bulb is a caridoid. So I call it the main caridoid. That main caridoid's value is 1. If you don't believe it, look here. The main caridoid is here, and its value is 1. See? 1. Everybody can see that. With each smaller circle after it, the value doubles. 2, 4, 8. Now, do you want to talk about the waves that you see? They're actually not waves. It's just the illusion of the hollow. The hollow makes you think it's waves. But actually, after we remove the hollow and go to the infinity iteration, it looks like this. You see how this is the biggest one? It has a value of 3. Who said that? I don't know. 6, 9, 9, 12, 12. The middles are added together. 4, 5, 6, 7, 8. You see the pattern. 3, 5, 7, 9, 11, 13. I bet you also see the pattern. Now, in between is the sum. 3 plus 4 equals 7. 3 plus 8. 3 plus 5 equals 8. 5 plus 7 equals 12, and so on. The same thing. On this side, you add 2s. On that side, you add 4s. Smaller and smaller. until... Wait, do you see these little caridoids? This is of the 1's control. This is of the 2's control. This is of the 4's control. Actually, they should just be all one color. 3, 6, 12. Anyway, this one is the 2nd caridoid. It's the 2nd caridoid you see. It's officially controlled by the 1. It's the 3 caridoid. Now, if you zoom on onto the 3rd caridoid you see, you'll actually get the 5 caridoids and 7th and 9th, and who says so? If you don't believe me, I'm going to show you a clip and you'll believe me. Well, actually not that fast, you know. To A0 to 0.5, actually any value will do. Pretty cool, huh? These blue lines, I programmed them to appear at certain times. Now rabbits become extinct. It took 7 days to work this out. Rabbits are still extinct. Rabbits still become extinct. Rabbits still become extinct? No. Rabbits are now extinct now. Starting to oscillate. Something weird is happening. Oscillate, not approach. Finally split into 2 different values. 4, A, 16, a little chaotic. At this point it's in 3s. No, it's not. Fine. You've seen the whole clip. Do you believe me? Probably not, but you will if you know what that means. Yeah. Quick view. I'm going to show you somewhere very important. The dancing of the 3s. That's why the 2nd caridoid is more like 3-like. Fine, if you still don't believe me, I'm going to play this clip again, but with a red note. And it's something different. It's called a cobweb. Don't understand, huh? Now you do. I expect you to. Wow, you're probably saying, how did you get this to go out? Once again, it took me 7 days. Now we're into 6. There's no cobweb. After that, the cobweb is going the other way. Which means that it's going to go chaotic pretty soon. Right about now. Yeah, fine. I'm going to switch this to the same value, 3.83. Oscillating as 3, majestical. Fine, now do you believe me? If not, I'm going to show you something more. Huh? What's that? You're probably saying. Take a look at the positive side. I installed a picture. Take a look at this side. So it's like, this is a period where, actually it's just a distortion of the Mandelbrot set. This is the first main bulb. Well, this is the, actually it's just like putting the Mandelbrot set in 3 dimensions and then taking a view from the other side. No, this is like the first circle, second one, third one, fourth one. They go quite quickly until they become chaotic. Until you finally, after the needle, see that there's another caradoid controlled by number 1. This is this line. 3, 6, 12, 24, and quickly chaotic again, 5, 7, and then finally ends. I don't know what value they took this for, but I know that they didn't take it for 0.5, a special occasion where 2 was not chaotic. For most of them, 2 will be chaotic. So now I'm going to explain why this is like the main bulb. It's just like, wait, have you ever known that this was a times table? Okay, fine, just take any bar. For example, this one. Only one end will work. Now, if you click on one end, you might be lucky enough to find the right one. Click on 2 and then you'll definitely find it. For example, if I click on this one, I'm lucky. The smaller number is 41. And 41 is one of the numbers on this end. And 2 times 41 is one of the numbers on this end. But why do they create this Mandelbrot illusion? Basically, we're multiplying by 2, and that is the biggest bulb on 2. Are you sure? It's a famous shape called a caradoid. It looks sort of like a upside down heart if you're creative. Now it's not upside down. The caradoid is just the outside part again. Like if I do search like the 16TT2. It's not very rough, though. I aligned this in orange lines and orange points. The caradoid is only the part surrounded by the orange points. Roughly. You know, like magic. No, not like magic, but if you put a circular mirror all the way around a space and put a light on one end, then when you look from above, then you'll actually see this shape. It's one of the 2 seeable shapes in a coffee cup. The fact is true, but the name, I just made it up. Because that exactly describes what it is. The caradoid is cool. Though we are talking about Mandelbrot set 2, I'm going to peek into Mandelbrot set 3. Because it also has a cool connection with the caradoid. I only did it to 10 iterations and it was like pretty. I already know what it's going to be like. Actually, not because of that. I already know what it's going to be like because I already looked at an image of it to the near infinity iteration. Not very near. But hey, look. When it goes to the infinity iteration, these will separate apart. And this part with all the other thingies will also separate apart. So this part itself is a caradoid. Same for the other size since all Mandelbrot sets are reflective across the real axis. So not always reflective across the imaginary axes, but when the y that I was talking about in video 1, that is x to the what, the z n to the what power, when it is odd, it's reflective along both axes. When it's even, it's reflective only along the real axes, because that means that the imaginary axes, well, it never matters. You know how in my introduction to algebra textbook, it says that for imaginary, it doesn't really matter positive or negative. Hey, look, it's just iteration 20 and they're cutting off. It's just iteration 20 and they're cutting off the hollow. No, this is only to a low resolution. Very low iteration. Low resolution. Because they haven't quite resolved it yet. Here comes the light show. See how the inner part changes color? That is because for the last few iterations, they are all very alike. It just varies the color. Coming back to here, probably very excited about video number 4. You know why, I think? Because it's like when you see video number 4, you see flowers. Not kidding you, there's actually flowers. A 3-petal flower in the center of Mandelbrot set 4. That is because 3 plus 1 equals 4. You know, it's always fun to add more iterations. Especially here. Like, no one will mind if I just add 6 more iterations, because this is my drawing of what I like. You know, we are starting to use the depth 3 colors. I'm never going to use any grayish color. No one minds if I add 6 more iterations. I'm going to call this color 25. I'll show an image of what color 25 looks like. Pretty good to add. Actually, each time I just take the next color generated by a system. This is how I create new iterations. I already got the platform set out. Each time I just add one more this on this side and one more this on this side. Complete. Now I'm going to change the settings, because for each one there has to be 0.5 fill of lines, 1 thickness of line, 0.25 of this. You know, it's not really defined on this computer as the border. There's no obvious border. unless you zoom in up very close on certain areas. Like this. Pretty beautiful. I tried printing a picture of it once and it turned out very well. So that time it was only to the 15th iteration. No one minds if I add another iteration. You know, it's pretty fun talking about that. So now let's see some pictures of it. You know, I searched this up on the Wikipedia. You know, I pretty much like this. It's like, you know, you can color a Mandelbrot that's outside by how quickly they blow up. See, like this. Again. Cool. Detail. Pretty much like the Julia set. Zoom in. It's okay if you didn't catch this. Another time. They're not cool. Whoa. Whoa. I've seen this many times. But each time the image of the Mandelbrot set is actually distorted. Each image of the Mandelbrot set is slightly distorted. That was the first image that was published. See, this is how the logistic map matches up with the Mandelbrot set. Though it looks completely disastrously wrong. They are actually a combo pair. 2D, 3D. Whoa. Basically, picture. This one we need to zoom in up close. It's the Julia set. You know that is related to the Mandelbrot set. It actually looks very like self-similarity. You know what the frigging bomb ratio? Not a bomb. The view magnifies from 0.5 times 0.5 to 0.12 times 0.12 to approximate the Fresnel bomb ratio, which is just like, well, this is a start. Mandelbrot set, well, pretty much like the one we, yeah. This is the gap between the main caridoid and the main circle. Also called the seahorse valley. Actually, every gap is a seahorse valley. We're just liking to zoom up and double spirals on the left. Seahorses on the right. Upside down seahorse. Yeah, all the seahorses are upside down. So this endpoint of the seahorse tail is also a Mizrax point. There's only one path that will lead through the whole tail. It's just simply connected. Look, the seahorse tails, many seahorse tails are in here in the seahorse tail. Cool. Between two tails. Cool. Look at the Mandelbrot, though it's a little distorted. This is call it antenna of the satellite. It's really like a Mandelbrot set. Pretty much. The seahorse valley of the, come on. We're zooming up into a different part. This is second order. I call it second order. This website calls it second order. This is a double spiral. This time we are going to zoom in into the double spirals. Are we? We are. They look like Julia set. Double hook on the right side. Yeah, probably there. Whoa, cool. This is the island. This is one island. This is the spiral. That's all. You can have Mandelbrot sets of different numbers, even decimal numbers. This is what it looks like. Like someone is poo-poo. But they go quicker and quicker. Yeah, there could be a 4D Mandelbrot. Actually goes into tricorn. Cool, let's play this. It's like there's a part of it, they call it the nautilus. And then you just add on iterations and this is what it looks like. There's basically no difference. All you see is a spiral. A few spirals. This is so much fun. iteration 1, 2, 3, 4, 5, 6, 7. No, iteration 1, 2, no, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 15. Because actually I took the photograph of the iteration 15 first because I did it before I actually got the 16th iteration. These are, well, pretty much a few of the logistic map thing. Actually, you know, I can play it for you if you want. It's pretty quick. Time versus population actually has a long name. Why is it red? Time versus population relation, rate versus equal population. Present. I use Canvas for this. Look, here's the, well, chaos part of the logistic map. Here's a whole one starting from 2.4 and ending at 4. Just an image. For this one, I chose some special number. And I changed it. Get 2 oscillating numbers, turning into 4. No, it's not 8, as you guessed. Chaotic! After 3.57, I didn't put in the one with oscillating groups of 3s. Maybe I should put in the Mandelbrot set. You know what? I think so. Upload. Brasset iteration 16. I'm going to take a picture of the iteration 25, you know. I'm going to get all those stuff out of the way. Actually, I have a separate picture way. I take pictures. First, I zero out everything. Basically, like only the Mandelbrot set. But then I add on the grid. No minor grid lines, no axis numbers. Zoom out. If I try 6s, I just want the main grid to be smaller. Good. This 6 is good. Here I go. Now I'm going to unfull screen this. Where is the picture that I just took? Here. love this 20. Gonna love this 25th iteration. Gonna do some math. It's going to 512. So basically I'm just gonna turn this into 512. by right in the middle. Gonna add some text. Actually, you know what? I'm going to cheat and add a subheading. Guessing it's in white. It's to the 25th iteration. I'm really good at this sort of stuff. Good crafting. You know, I always have the guessing in store. I actually got a presentation on almost everything. I have one on primes. I have a lot of designs. I have one on the Mandelbrot set, of course. 20 slides. Prime thread to do 10. It's sort of a 2-page chart. Steve, I didn't do it yet. 3x plus 1. I don't know why I keep making 4x3 presentations. 9x16 presentations are better. I think I got more. All my projects. They don't have to be designs, you know. This is a multiplication chart. There's 3x plus 1. That's an interesting Pascal's triangle. The one I just made, one about primes. That's all. They relate to almost everything. Know why? They relate to math, and math relates to everything. I'm smart, right? This is my color source. Look at all my colors. Guess how many I have? What? How many did you guess? The correct answer is 43. I'm going to make that number 125 pretty soon. This is a good starting point. It's not yet the end. It's just the start. There must be something related with the Tower of Hanoi if I'm showing it. Oh yeah, it's just the color source. Come on. How come I didn't even realize that? I really like the Mandelbrot set. Really. Oh yeah, here's the picture just for your reference. I see the Caradoid. No one will mind if I just add 2 more iterations. It's so much fun that I just can't stop it. No one will mind. No one will mind. How come I always type in 225, not 255? That's basic. What was I thinking of again? Oh yeah. How come I was thinking of that? Fine. I'm going to do it again. Actually, I'm going to do one more. Because here's the iteration 0, right? No. I always like to make things nice. 12 is a nice number. No, guess how many lines of decimals I used? 128. That's a lot of lines. Here's my color source. Oh, how I love it. Copy. Paste. That was quick. More importantly, that was fun. I'm going to make 3 more iterations just to make sure that you actually see the Caradoid. Make sure it follows the pattern. Actually, I'm going to do YouTube just to make sure you have fun. Why is this always so slow? I have a lot of information processing, huh? Yeah, now what should I... Oh yeah, logger. Fine, I think I did this somewhere else. It's 13 minutes.
Okay, so to start off, I've got four images for you. So look at them. 1, 2,
They use animation.
4. Now, quick question: would all of them have in common? Well, I would be really surprised if you guessed this one here.
They're full of lines.
Huh?
They're full of lines.
They're full of lines and they're in a
Oh
circle.
yeah, that's exactly what I was guessing
but
the
actually
first
pictures
time.
of times tables.
Huh?
Ah, okay.
Most
Pictures
people
of
are
times
like,
tables. I better explain
huh?
this, alright?
Except
So
if you
to
watch
get
my
these
earlier
pictures, what you do
videos.
is you start with a circle, and then you pick a random number. Okay, and we'll just choose something nice.
yeah.
We'll start with a 10.
10.
Okay? So then with 10 we put 10 points on the perimeter here, equally spaced, and then we label them with 1, 2, 3, 4, 5, 6, 7. Okay, let's just go. Actually, we start with 0, 0, 1, 2, 3, 4, 5, 6, 7.
This is
8,
really
9.
getting silly.
And 10 we also want, so we kind of put that right there again. So that's also 10, that's also 11, 12, 13, 14, 15, and so on. Okay?
You just
And then again.
stop here.
And
Duh.
so on. Right? So this guy here stands for 1, 11, 21, 31, and so on.
And you
Okay?
can get anything one.
And now we're going to do the 2 times table. Okay, the 2 times table. And we'll start with
This is a fun
0.
part.
So 2 times 0 is?
0.
So 0 is the same thing, so we don't do anything. Okay, 2 times 1 is?
2.
2. Okay, so we'll connect the 1 to the 2. Then 2 times 2 is?
4.
Okay, we do this.
They
and
have
we keep
someone
on
else.
going. Pretty obvious. Now 5. 2 times 5 is? 10. 10, remember, 10 is also over there, so we connect that guy up. And then 2
Basically
times
just
6
mirror
is 12, which is also the 2. So we connect that one, and you kind of just keep on going like this. Okay? And then you're at 9, and you've pretty much gone all the way around. Now you could go on. So for example, we could now do 2 times 10, and 2 times 11, and 2 times 12, and
It's
draw
just the
in
same
those
thing.
connections. But actually, the connections are going to be exactly the ones that we've already drawn. So we can actually stop here. Just to illustrate, let's just go up to 2. 2 times 12 is? 24, which corresponds to the 4, and that connection is already there, right? And 2 times 13 is? Not quite. 2 times 13?
2 times 13,
26.
You put
and
that
we've already got
36.
Of course, we made a choice there at the beginning, that 10, right? If you change that 10 to anything else, well, the picture changes, but pretty much everything I said stays the same.
It's
Okay?
going to
So, for example, if you switch from 10 to 11, we get this guy here. And then
12.
13, 14,
It's starting to form.
15, and let's just see what happens. Pretty nice.
Yeah, that's exactly what I was
They
waiting for.
are symmetric
Yeah,
in the horizontal axis.
that's right. Yeah.
Is that for a particular reason?
Yep, there's a reason, and actually let's just give this as homework for our guys here to figure out. So in the comments, tell us why there's a symmetry. Of course, what's much more interesting here is that curve that somehow magically
Boring.
materializes when you kind of
I
up
already
the
know
number
why.
that you choose at the beginning. Okay, and actually
Gonna
I'll just highlight it a bit. So there's this strange curve here. It's actually got a name.
You know, I'm going to tell you why. Because, well, k minus n, you know, k minus n is a little bit like minus 2n mod k. 2 times k minus n. It's like a minus 2n. And minus 2n is like just you go, well, too far. That's
It
it.
pops up all over mathematics. It's called a cardioid.
Back into
like
Mandelbrot.
cardiology means heart.
And that's
It's
exactly
like
the
a heart, so
reason
mathematical heart curve.
reason I
That's how
showed
we
you
draw
this.
it.
I'm going to
Places
show you
I'll
this
show a
again in
few.
the next
Okay.
video.
So for example, you can have it as a rolling
Whoa.
curve. You roll one circle around another circle, and just see what happens
there's a
to
faint
one
line.
of the points on the boundary of the rolling circle.
That's
Okay,
that
so
one.
here, and what it
It's
does
just
is
tracing the
it
faint
traces
line.
the cardioid. Okay. Now where else can you see it? Well, sometimes you can see it in your coffee cup. If you've got a conical coffee cup like this, and the sun is in the direction of one of those green lines in the coffee cup, then you can also see cardioid in there. Where else? Well, there, right there in
Oh,
the
yeah.
Mandelbrot set. So the biggest bulb in the Mandelbrot set is cardio. The second one is actually a perfect circle. Now,
Obviously.
this would be a good one to figure out why is this guy cardio? So just look
Yeah,
at trace this down somewhere.
why is it
Now,
cardio?
just for those people who know something about this stuff, that's the equation that we use to make up the Mandelbrot set. And there's
We're
a
almost
two in
hitting
there,
1
okay? So that's
hour
important.
long.
We just had the 2 times table. Let's just keep going, okay?
It's more
Now,
like a popcorn
yeah.
movie.
Um,
3 times table!
Actually, a video producer, I know that microphones, there is a category of microphones called hardware microphones, and that's because they pick up the sound in that area, from that direction.
Okay, right. Well, maybe we'll do another video on this. Okay, now we can also, instead of doing the 2 times table, we can do the 3 times table.
Oh, yeah.
If we do the 3 times table, well, what we get is this pattern here for initial choice 10, and then I'll just, up the numbers there, and what do we get? Woo, another curve. Another very famous curve, which is called the nephroid, which is kidney. Okay, whereas this one is also the rolling curve. Here the circle that rolls is half the size of the one that is rolling round. It's also in a generalized Mandelbrot set. So remember, before
That's exactly
we had
the one I wanted to show
exponent 2
you.
here. Now we're talking about 3 times table. We change the exponent to 3, and you actually get the main bulb here being the nephroid. Okay.
Exactly what
You
I
also
want.
get it in a coffee cup. This time we need a straight coffee cup, and the light rays kind of come in like from one side. Okay, so they're kind of coming straight like this, and then they kind of bounce around inside the cup and make up this curve. Actually, this way of making up a curve is called a catacaustic in mathematics. So there we go. What else have we got? 4 times. Yeah, you can kind of see a pattern now.
Oh,
Get
3
to
petals.
3 petals. Before we had 3 times 2 petals. Okay, and then all these other things that we've kind of been highlighting here. There were 2 there. Exponents gone up to 4. There's the generalized Mandelbrot set here. Now we've got the rolling curve happening again, right? And then just for good measure, there's one more guy here. There's the 5. That goes 4 petals. And we've got the Mandelbrot set here. And we've got the rolling curve. So all very, very neat, okay?
So the number of petals.
Wait, I just wanted to show you these generalized Mandelbrot sets, like the nephroid. Cool to go in detail. Just like you're extracting main bulbs. This generalized Mandelbrot set is like, when I see this, I'll be like, where did the nephroid go? The truth is that there's no nephroid. Huh? I probably... Fine, I'm going to rewatch.
Right here, that's the 5. So it has 4 petals. And we've got...
Yeah, this is a cool one to look at. Why is it square?
Mandelbrot set here, and we've got the rolling curve. So all very, very neat, okay?
So the number of petals is n minus 1.
Yep, n minus 1. And it keeps on going like this, so there's a pattern like this.
Why is
Okay,
there a
so
big
let's just start
duck?
again with 2. Okay, so that was 2 times table. Now one really nice thing to try is actually make the increments not 1 to 3 to 4 to 5, but actually do smaller increments. Okay, or actually do the transition here continuously. So let's show you, if I just do the multiplication times 2.1, what do you get? 2.1, 2.2, 2.3, 2.4, 2.5, 2.6,
Starting to
2.7,
make
2.8,
another.
2.9, and 3. And you can kind of see how the cardio turns into this nephroid, which is kind of cool, huh? And now I just let it go, and the numbers are going up, and you can see the petals going more and more and more and more, right? So just continuously. And when you think, well, that's probably what it's going to be, you can also look at this in the Mandelbrot set, and you can actually see exactly this sort of pattern here happening in the middle. And if you kind of push the exponent to infinity, the whole thing kind of turns into one big circle. That's pretty cool. Okay, and that's, I think that's the end of it, but no. Let's just keep going here, right? So the petals are pretty much going to go away now. But if you just look at what's happening here, you see there's a lot more, structure somehow being hinted at, right? I mean, we're moving very fast at the moment, right? We're moving very fast. But if you actually went through this frame by frame, you would see a lot of really, really nice structure happening. And I've highlighted a bit here. So just a few of the frames that...
Yeah, these are a few, like 21, 29, 33, 34, 49, 51, 66, 67, 73, 76, 79, 80, 85, probably 86, 91, and 99. I got 20 out of 20 on my eyesight. I'm really good at
There's
this.
some really amazing stuff happening here. So if you stop at 33, you get this one here. Stop at 34, you get that one here. And there's a couple of other highlights here. There's a lot more. So this is how many I could fit here. Huh? Okay, and maybe have a close look at some of them. Okay. So here we've got 4.
It's 2, 34, 51, and 99. The 2 is like the caradoid. Well, we use 200 dots. The 34 is like cool, 2 caradoids joining together. 51 is pretty circular. 99 is like, whoa, chessboard.
What? Now the number that all these correspond to is actually 200. Okay, 200. What we're really doing here has a special name in mathematics. Okay, so what we're really doing here is we're doing the times table modulo 200. Okay, so it's got a special name. It's actually incredibly important in all sorts of applications to do this sort of modular arithmetic. Okay, but anyway, for our purposes, you understand how it's built up, and if you know a little bit more, you know a little bit more. Okay, so for 2 times table, we get the cardioid. For the 34 times table, modulo 200, we get this guy here. And then some other things, interesting things happen. So for example, if you multiply by 51, we get this guy here. And if you multiply by 99, we get that guy here. And obviously, I mean, if you just look at the 2 numbers here below, 51 is pretty close to 1/4 of 200, so it must have something to do with that. 99 is pretty close to 1/2 of 200. Something to do with that.
The pattern is that, wait. The pattern is that each time this is obtained by 1/4 of it plus 1, and this is obtained by 1/2 of it minus 1.
Now, I really wanted to explain something. I really want to explain where this one here comes from. And, well, I mean, the first time I saw this, I was pretty surprised, like pretty much everybody had seen it, but then I remembered something. I had seen a cardioid before in, many, many different guises. And in one particular one that I was familiar with, I could see where the connection is. And I just want to tell you about that one, okay? And it's got to do with this light rays bouncing around. It's a little bit different from what we had before, okay? So basically we've got a circle here, and then we've got a light source right over on that side, right? And that circle kind of reflects the light, right? So we switch on the light over there, and then, well, what happens? Well, light rays kind of emanate in all kinds of directions, get reflected off the circle, right? Bounce around, and you kind of see this pattern here emerging, the cardioid. Right? So I knew this one. I had actually calculated the curve from this prescription at some point in university, okay? Then they can actually really see very easily why the cardioid comes up in the 2 times table. And I want to show you, okay? So let's just highlight like one of those rays coming out. It kind of hits the wall here, okay? And then it gets reflected at the same angle as it comes in, right? So this angle here that you see here is the same as there, right? You can see it kind of goes like that. Okay, so what does that tell us now? Well, if we put this line here in the middle, it means that this side really flips over to that side. Which means that
light ray reflects off a circular
is
curve.
exactly as long as that one here, right? So if I travel from
0
from
and
this
2
light
n.
bulb to this point, and then from this point
I watched
to
it
that point,
multiple
it's exactly the
times.
same distance, okay? So that's going to be important.
I already
Okay,
know what
so
happened.
let's make this 0. Let's call this n. So what's 2n then, right? So to get 2n, what you have to do is you have to measure this distance here, and then you have to measure it again, Where do we get? Right up there. And so it's pretty clear that when you do a 2 times thing, you get that reflected ray, in the picture. Just to finish off, I'm going to show you a little bit of a movie of all this stuff evolving a little bit slower.
We are starting with 0. Here it comes. 0. Start. I'm going to tell you when to start looking in the middle. The yellow is a little bright. Now you can start sort of looking in the middle. It's making very noisy stuff. Look in the middle. Patterns start to happen in the middle. It goes pretty quick. Whoa, flower spiraling. Again, whoa, again and again and again and again and again. I'm just going to stop saying again. I just said it. That's pretty much what happens when you hit 51. But it's when you hit 51, not when you hit 199. 199 is like the theoretical limit. Pretty cool movie, huh? It's like 13.5 minutes long. You can share this link in the description if you want. This is pretty cool. Mandelbrot set again. See that keratoid. Well, now obviously. Mandelbrot, please. I'm still not sure if you saw that nephroid. Fine, if you don't, then I'm going to highlight it. Yeah, I'm going to highlight it with black paint. It's like here. So it basically goes like this, and then this on both sides. You have any questions? If yes, then you can ask in the chat. So like, I'm going to wait. See how this nephroid? See how this Mandelbrot set 2 evolved? I'm going to turn off annotation first. See how this set evolved? Okay, now this is pretty much, I'm going to start pretty soon. Actually, what you call the Mandelbrot set to the 25th iteration is actually only this red part. And I'm going to zero out this red part also. Doing square again. So this is how the Mandelbrot set evolves. Because my presentation only has 16 iterations, but only right here I have more. So step 1, C, big circle, limit. Now it has an oval hitting 1.5 at the most. A smaller hammerhead. This is not the curve of the real thing. How it starts to straighten itself up here and the part on the. So see how, actually I like annotation. This part becomes straight and this part becomes thin. Again, even thinner, and this starts to curve backwards as it does in the real one. Even thinner. Actually, you know what? I'll take you on a trip to what is happening over here. This is the interesting part. They'll have pretty much iterations. Go quickly through here. See now on this iteration it starts to be big. I'm going to take you here. This is the only interesting part over here. Start to evolve. As other sections evolve, I'm going to show you both of these. This is 3 ball bands of 5. They both evolve. This one quicker because that one was bigger. Evolve again, and 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 again. Now this part finally looks like the Mandelbrot set. Huh? This web thingy is really slow. I'm going to start it over, but on the other side this time. Like this. I'm going to do it again, but this time yeah, pretty much like that. I'm gonna show a little more. Then like that. See how the Mandelbrot set quickly evolved from the There's little wave patterns. When the hollow illusions disappear, they're having little islands. Each iteration gets closer by a smaller amount because they take up most of the way to the fractal. You know, a little bit like this. With each iteration, these come closer together. So this one is pretty much like a measuring tool that tells you when or what iteration you are on, approximately. Almost to the last iteration. Now this is the last iteration. Now we put a lot of work into it, though the picture iterations go up to 25. I'm going to turn something on. Something else. No, not this. This doesn't change it. This takes a little. Now we have these points. Now you just do this over and over again. This. Now it's in the Mandelbrot. Wait, I thought you could move this. Oh yeah. This is getting a little slow. You can move this. When it's inside here, the 15th iteration will be in here.
Oops, sorry.
And when it's not, even by only a little bit, the 15th. Actually, you know what? I'll zero out all the higher iterations beyond 15. 24, 23, 22, 21, 20, 19, 18, 17, 16. This must be iteration 50. When it's outside, number 15 will not be in here. The smallest shape it is indicates the last dot that is still in there. When it's out of here, even just a tiny bit, now it's just a tiny bit from out, but it's still in. is out, so the whole thing is out. Point. This is pretty much all about the Mandelbrot set 2, video 2. Is that a coincidence? Bye.